Good day, everyone. I am Nicole Ann Alido. Together with my groupmates Hanna, Lucero, and Shannen Pelpinosas, we will be discussing about pure substance. First, let us define what is pure substance. Everything that exists on Earth is a form of a matter which is defined as any substance that occupies space and has mass. As shown in the image, matter can be divided into various forms, such as solid, liquid, and gas, and it can be further classified into mixtures or pure substances. A pure substance can be either an element or a compound. Pure substance is a substance that is made up of only one kind of particles and has a fixed or constant structure. Pure substances are mostly homogeneous in nature, containing only one type of atoms or molecules. These substances mainly have a constant or uniform composition throughout. These substances also has fixed boiling and melting points. In short, a pure substance is a substance which has a constant physical and chemical properties. Examples of pure substances. An element is a pure substance as it cannot be broken down or transformed into a new substance even by using some physical or chemical methods. Examples are gold, copper, oxygen, chlorine, and diamond. Compounds are also pure substances when two or more elements are combined chemically in a fixed ratio. However, these substances can be broken down into separate elements by chemical methods. Some of the examples are water, salt, and baking soda. So for water, it is made up of one oxygen and two hydrogen atoms, which are two different elements that is combined in a fixed ratio which is 1:2. Comparison of three types of matter. As what I've said earlier, matter is divided into three different forms. Now, let us compare those. So for solid, solid has a strong molecular forces, has a definite shape and volume, least compressibility, and does not flow, while liquid has a weak intermolecular force and acquire the shape of the container, defined volume, and its compressibility is in between solid and gas, which is higher than that of solid but lesser than gas. And unlike solid, liquid can flow easily. Lastly, for the gas, its intermolecular forces are negligible, and similar to liquid, it takes up the shape of the container, but it changes its volume to fill the container. It is highly compressible and it flows easily. Here is a better view of the different phases of matter. The solid have the strongest molecular bonds among the three and are closely packed together. Also, its molecules do not move relative to each other. Next is the liquid, which has the intermediate molecular bond strength. Its spacing is comparable to solids, but their molecules can float about in groups. So for gas, it has the weakest molecular bond strength, where its molecules are far apart and they have no ordered structure. The molecules move randomly and collide with each other. Before proceeding to the next topic, let me define first the following terms for better understanding to the discussion later on. First, saturated, a condition in which a mixture of vapor and liquid can exist together at a given temperature and pressure. The temperature at which vaporization or boiling starts to occur for a given pressure is called the saturation temperature or boiling point. Next is compressed or subcooled liquid, phase of a substance that is not about to vaporize. Next is vapor, gas phase at a substance where the same substance can also exist in the liquid or solid state, below the critical temperature of the substance. Next is superheated vapor, vapor heated to and beyond its normal boiling point at atmospheric pressure. And last is saturation pressure, is the pressure at which the liquid and vapor are in equilibrium at a given temperature.
Hi, good day. I am Hanna Lucero, and I will be talking about the properties and phase change of pure substances. Also, we're also going to talk about the diagrams, the property diagrams for this topic. Now that you have learned the terms that we will be needing for this topic, let's get to learn the properties of pure substances first. Again, pure substances are matters that can be divided into various forms such as solid, liquid, gas, and then can be further classified into mixtures or pure substances. A pure substance can either be an element or a compound. Pure substances covers the following properties, namely saturated liquid, saturated vapor states, saturated liquid, vapor mixture, superheated vapor, and compressed liquid. Before diving deeper into these properties, let's have a gist of what phase change processes are, because this will provide us more information on these terms or the properties. So the following are the state of the phase change properties of pure substances. So phase change processes of pure substances includes the very first state, or the state 1, the compressed liquid or the subcooled liquid. This liquid is a substance that it is not about to vaporize. Water is at 20 degrees Celsius. It is at its liquid phase or its compressible liquid. That means it's 100% liquid. That's what happened at state 1. At state 2, this is where the liquid is about to vaporize. So at state 2, we call that the state where it is a saturated liquid. So state 2 is an increase in temperature from 20 degrees to 100 degrees Celsius. So it's more than 20 degrees Celsius, but it's getting to 100 degrees Celsius. It is due to the application of heat here, and at constant volume, phase of the water becomes a saturated liquid. So here at 1 atm pressure at 100 degrees Celsius, water exists as liquid ready to become a vapor. So it's going to be a vaporized liquid, which is what we call a saturated liquid. So at state 3, so this is where the continuing application of heat to the system. So saturated liquid of the pure substance will vaporize. This is the time where it's going to it's going to vaporize, and it will convert to a saturated vapor. At this state, some of the pure substance is in liquid molecules expands to gaseous or vapor. So here, as more heat is transferred, part of the saturated liquid vaporizes. So it becomes a saturated liquid and vapor mixture at state 3. So a saturated liquid vapor mixture, this is where the state at which the liquid and vapor phases coexist in equilibrium. So at state 4, So this is where the 1 atm pressure, atmospheric pressure, the temperature remains constant at 100 degrees Celsius. Though in the graph, I will show you later. So there will be a constant graph because this is where the vapor is about to condense. So the saturated vapor, this is where the last drop of the liquid is vaporized. Not about to, but is vaporized. So this is where the graph shows a constant line. So the state 5, this is where the vapor is not about to condense. So this is what we call the superheated vapor. So this is the peak of the graph. So this is more heat is transferred, the temperature of the vapor starts to rise. So that is the superheated vapor. So this is the graph that I want to show you. This is the relationship entirely of the first to the fifth state. So they're describing the reverse. They're describing the graph from the compressed liquid state until the superheated state. The entire process between state 1 and 5 described in the figure is reversed by cooling the water while maintaining the pressure at the same value. The water will go back to state 1, tracing the same path. In doing so, an amount of heat released will exactly match the amount of heat added during the heating process. To give you a more detailed look at this graph, so this is the graph that I wanted to explain to you or to show you. So at compressed liquid state, it is 20 degrees Celsius. So this is where the substance is not about to vaporize. That is a compressed liquid state. So when it comes to this state, at the point where the rising graph and the constant one is the constant temperature meet, that's where the saturated liquid comes. So this is where the liquid is just about to vaporize. So when the temperature is at constant, that is the saturated mixture, this line here, it is a state where the liquid and the vapor phase coexist in equilibrium. So at the stage where the saturated vapor is about to come, the stage 4, the saturated vapor, this is where the last drop of water is just about to boil until it reaches the fifth state, which is the superheated vapor. So this is a vapor that is not about to condense. I will be giving you a summary of the properties of pure substance. So saturated liquid about to vaporize. So it's water at 100 degrees Celsius at 1 atmospheric pressure. So saturated vapor about to condense, water vapor or steam at 100 degrees Celsius and at 1 atmospheric pressure. Then superheated vapor not about to condense is water vapor steam at more than 100 degrees Celsius and 1 atm. Compressed liquid, this is not about to vaporize, so it is called subcooled liquid, and the water is at 20 degrees Celsius and 1 atmospheric pressure. So this diagram is the relationship between the temperature and volume for the heating water at constant pressure. But this time, the saturated liquid and saturated vapor are known as the V sub F and the V sub G, where the saturated mixture will have the formula of V sub G minus V sub F. Here, the relationship between the saturated liquid vapor mixture of pure substances is a curve form, in a curve relationship. So I will be explaining to you the critical point later on in the next slides. So the saturated vapor, the Vg, and the saturated liquid, the Vf, is equal to the UAV, or the saturated liquid vapor mixture. So the saturated liquid vapor mixture is during vaporization, a mixture of part liquid and part vapor exists. To analyze this mixture, we need to know the proportions of the liquid and the vapor in the mixture. So the ratio of mass of vapor to the mass of the total mixture is called quality X. So X is equals to the mass of vapor over the mass of total mixture. So this is M total equals M liquid plus M vapor equals M sub F plus M sub G. So these are the terms that you need to know. Latent heat, the amount of energy absorbed or released during a phase change process. Latent heat of fusion, the amount of energy absorbed during melting. It is equivalent to the amount of energy during freezing. So latent heat of vaporization, the amount of energy absorbed during vaporization, and it is equivalent to the energy released during condensation. Sensible heat, energy required to change the temperature of a substance with no phase change. Let's proceed to saturation temperature and saturation pressure. So the temperature of which the water starts to boil is actually depends on the pressure. So if the pressure is fixed, so is the boiling temperature. We all know that the 100 degrees Celsius is the boiling point of water at 180 atmosphere pressure. So saturation temperature, so it is denoted as Tsat, the temperature which is a pure substance change given pressure. Saturation pressure, denoted as P sub sat, the pressure at which a pure substance change phase at a given temperature. So these are the two property diagrams of pure substances, relationship of the temperature to volume and pressure to volume. I'll be explaining the terms included in this diagram. The atmospheric pressure increases, also the line of the diagram also changes. And that's where we hit a common denominator among the diagrams. So first is critical point, in which the same for the both diagrams is the endpoint of the phase equilibrium curve. The most prominent example is the liquid vapor critical point. So the endpoint of the pressure temperature curve that designates condition under the liquid and vapor that can coexist. So these are the terms that you need to know for the diagram. So the critical point is the endpoint of the phase for every equilibrium curve. So this is the critical point for the property diagrams of pure substances. It is a saturated liquid line. So this is the left side of the curve. So it is established for the values of the saturated liquid for a given property. So this is the left side for both region. Next is the compressed liquid region, the region to the left of the saturated liquid line and the below critical temperature that is called compressed liquid region. Saturated vapor line, the right side of the curve, this is established for all saturated vapor for a given property. Saturated liquid vapor region, this is the region between the saturated liquid line and the saturated vapor line. Heated region, the region to the right of the saturated vapor line and above critical temperature. Terms that you only need to know for the pure substances.
Good day, everyone. I am Shannon Angela A. Pelpinosas. My topic for today is a brief discussion about what is enthalpy, and I am going to give some simple problem examples afterward. So sit back and enjoy my report. So what is enthalpy? Enthalpy is defined as the sum of the internal energy and the product of the pressure and its volume. Based on the definition, enthalpy simply means the heat content of a system at a constant pressure. It is given by the equation H is equal to E plus PV, where H is the enthalpy, E is the internal energy, P is the pressure, and V is the volume of the substance. The change in enthalpy of a system happens when heat is added to the system or heat is decreased. This is more commonly called as enthalpy change, with a given formula of delta H is equal to delta E plus P delta V. Adding on, if the change of enthalpy in a system is negative, then it would mean that the reaction was exothermic, since the system released more energy than what is absorbed. The opposite of that would then be endothermic, where the system absorbs more energy than what was released. So enthalpy is useful in several fields like biology, chemistry, and engineering, which makes use of the concept of enthalpy, as is it the major factor which determines the power output of machines, reactions between two substances, as well as in forensics in investigating the crime scene. Enthalpy plays a huge role in these areas. Moving on, let's talk about the importance of enthalpy. So for this part, I listed five main importance of enthalpy. The first importance is by measuring the change in enthalpy in certain reactions, we are able to determine whether the reaction is exothermic, released heat, a negative change in enthalpy, or endothermic, where it absorbed heat, it is a positive change in enthalpy. Knowing this type of reaction is important, especially in the field of forensic science, as well as during fires and explosions, as knowing what caused the incident to happen plays a crucial role into the completion of the case itself. The second importance is it is used to calculate the heat of the reaction of a chemical process. Certain chemicals react with other chemicals in different ways, as such being able to calculate the heat of reaction which uses the concept of enthalpy. By knowing their heat of reactions, we are able to construct certain precautions as well as study them as to avoid unwanted reactions that may cause harm or danger. Third importance of enthalpy is change in enthalpy is used to measure heat flow in calorimetry. Calorimetry plays a huge role in several fields of engineering and industry. In civil engineering alone, tests and tools such as calorimeters are utilized for research, mix designs, determination of potential material incompatibility, as well as inferring physical properties such as compressive strength and setting times. Fourth importance of enthalpy is enthalpy is used to calculate minimum power for a compression. So the enthalpy or heat content plays a major role in the efficiency and performance of the compressor as well as the maximum and minimum power it can input. Temperature and pressure as well as gas properties behave differently when subjected into different temperature change due to enthalpy. Therefore, these are factors which must be taken into account as well. Lastly, the fifth importance of enthalpy is enthalpy change occurs during a change in the state of matter. So, matter changes its states when subjected in increase or decrease in temperature. As such, measuring the enthalpy in a given system is important as this will determine the heat capacity of the functionality of the certain material, especially when it reaches the threshold. Okay, for the next part, we're going to solve simple problems. So, sample problem number one. Hydrogen peroxide decomposes according to the following thermochemical reaction. So, hydrogen peroxide in liquid form yields to water in liquid form plus 1/2 mole of oxygen in gaseous form with a given enthalpy of negative 98.2 kilojoules. So, calculate the change in enthalpy delta H when 1.00 gram of hydrogen peroxide decomposes. Um, this problem requires that we find the change in enthalpy, given that 1 gram of hydrogen peroxide decomposes. So to solve this, first we are going to find the molar mass of hydrogen peroxide. So by solving using a periodic table, we get 34 grams per mole for hydrogen peroxide. Next, we are going to multiply the molar mass by the given mass of 1 gram. Then we're going to multiply it by the given enthalpy for hydrogen peroxide, which is negative 98.2 kilojoules per mole. Cancel like terms and we are left with negative 2.89 kilojoules as our delta H. Okay, moving on to our next problem. So, sample problem number 2 has two parts. Part 1, calculate the change in enthalpy, delta H, for these two processes. H2O in solid state yields H2O in liquid state, so find its change in enthalpy. The next process is H2O in liquid state yields to H2O in gaseous states. Also find the change in enthalpy. While in part B, using the values you calculated, find the number of grams of ice you can melt using 0.9 kilojoules of heat. So to tackle this problem, first we are going to solve for part A. So the heat of fusion and vaporization are in joules. So the first thing to do is convert it to kilojoules. So using the periodic table, we know that 1 mole of water H2O is 18.02 grams. Then we multiply it by the latent heat of fusion for water, which is 333 joules per 1 gram, which is 6 times 10 to the power of 3 joules, which is 6 kilojoules when converted. Next, we multiply 18.02 gram by the latent heat of vaporization for water, which is 2,257 joules per grams, which results to 4.07 times 10 to the power of 4 joules, which then converted to kilojoules is 40.7. So the completed thermochemical reactions are in H2O in solid states yields to H2O in liquid states. The um, enthalpy change is 6 kilojoules, while in H2O in liquid states that yields to H2O in gaseous states, and change in enthalpy is positive 40.7 kilojoules. Okay, so for the solution in part B, um, using the values you calculated, find the number of grams of ice you can melt using 0.8 kilojoules of heat. Now we know that 1 mole of water in solid state is equal to 18.02 grams, and its um, change in enthalpy is 6 kilojoules. Okay, I mean. So using this conversion factor, 0.8 kilojoules times 18.02 grams of ice per 6 kilojoules is equal to 2.4 grams ice melted. So for your answer for part B, it is 2.4 grams of ice melted using zero point 0.8 kilojoules of heat. Okay, so moving on our last problem, which calculate the change in internal energy when 2 moles of carbon monoxide are converted to 2 moles of CO2 at 1 atm and 25 degrees Celsius. So the thermochemical reaction is written as 2CO at gaseous form plus O2 in gaseous form yields to 2CO2 in gaseous form, and with an with an um, change in enthalpy of negative 566.0 kilojoule per mole. So to solve that, we are given the enthalpy change in delta H for the reaction and are asked to calculate the change in internal energy delta E. Therefore, we will need the equation 6.10, which states that It is another way to calculate the internal energy change of a gaseous reaction is to assume ideal gas behavior and constant temperature. So in this case, it is delta E equals delta H minus delta PV. Using ideal gas law, we will change PV to nRT. So our final equation would look like this. Um, Delta E is equal to delta H minus RT delta N. Okay, so from that, we will go on continue our solution. Okay, from the chemical equation, we can see that 3 moles of gas are converted to 2 moles of gases. So from here, so our reaction, we have 2 moles of CO and 1 mole of O2. So it's 3, and it yields to our product of 2 moles of CO2. So from that, um, the change in the number of mole is equal to number of moles of product gas minus the number of moles of reactant gas. So 2 minus 3 is equal to -1. So then, using 8.314 joules per Kelvin times mole for our R and T for and RT is 298 Kelvin. Um, we're gonna use this to substitute in our 6.10 equation. So we write um, delta E equals delta H minus RT delta N and substitute all given. That would be negative 566.0 kilojoule per mole for our delta H minus 8.314 joules per Kelvin times mole times 1 over 1 kilojoules over 1,000 joules. So we're going to convert that to kilojoules. Then multiplied by 298 Kelvin and -1 for the number of moles. So our final answer would be 563.5 kilojoules per mole. So that is all for my report. Thank you for listening and God bless.